Hello, here we will look at groups of small order. And we will look at them through their operation tables. They're called Cayley's tables. The group of size or order 1 is not interesting since it has to have a special element, the identity element. It will be just 8. The first group where something interesting happens is a group of order 2, and if we list elements, one of them will be the identity and the other will be something which we can call anything like, let's call it G. Then I'll just write down the table of operation on this group, the Cayley's table. I'll use multiplication for this operation, the dot. So I will just write the table, labeling columns and rows by my elements, and then at each intersection, in each position, I will just place the product of this element with that element in here, this element with that element in here, and so on. So the product of the row label and the column label in this order. When we multiply and when we compose with the identity, nothing happens, it's just the other element. So the identity labeled row is just the same as our list of elements. Sorry. And the same for the identity column. If we compose or multiply G with the identity in this order, we still have G. So the only interesting place is this position. It is the place for G squared. So let's just see what is G times G, or G squared. Well, we have two options, so only have two elements to choose from. So let's see what happens if we just choose it to be G. The special property every group has is division, is inverses, multiplying by inverses from the left or from the right. Can be thought of left to right division, and it leads to cancellation. So if we have the same multiple on the left on both sides of the equation, we can cancel it out. So cancelling it out, we will have the faulty conclusion that G is the same as identity. We chose them to be different. There are two different elements in our two-element group, so that is a contradiction. We cannot have the answer here being G, so it must be the identity. And indeed, it is a working group. We have, well, at least two examples. Integers mod 2 is a group of order 2, so the addition operation on congruence classes of 0 and 1 is 0, 1, 1, 0. Just like we have here if we think of E as 0 and G as 1. Another example will be, say, the group of plus and minus 1, which appears as roots of degree 2 of 1 in complex numbers, or invertible integers, or invertible integers modulo 3. They give the same group, and the elements are 1 and negative 1, and the multiplication table for them is indistinguishable from this table or from this generic template. So perhaps last incarnation of this is the symmetric group S2, the group of permutations. This time it's the composition which we are using as the operation, and I will draw pictures for the elements, the identity and non-identity, which is called transposition, and then the composition table will be again the only possible one. We just proved here that it is the only possible Cayley's table of size 2. So all groups of size 2 from this computation are bound to be the same, are bound to be what is called isomorphic. Upon relabeling, the operation becomes identified. So proceeding to the next order, the order 3, it would be good to have this sort of argument generalized a bit. And here is a generalization. So it's a fact about any size Cayley's group. Elements in a single row or column are bound to be different. So that is what we effectively used here. We already had G in this row, in the second row, so we must have identity as a second element in that row. Let's see why. Here's a quick proof. Let's assume that they are not. So what are elements in a given row, for example? If this row we're looking at is labeled by some element G, then two elements we will have products of G with something and then something else. And this cancellation property in a group will imply that these two other factors have to be the same, because we can multiply by G inverse both sides of this equation and effectively remove them. And that is a contradiction, because we assume, if we list these answers in a Cayley's table, we assume F and H to be different. So that is a proof that elements are always different in a given row or column. So let's use this and listing elements, so F and G this time, putting them as labels of our Cayley's table, and filling as much as we can using the identity rules. Let's see what we can put here. Well, in this row we already have F, and we have F again, so we can not put F again here. There will be too many F's in a single row or column. We can put identity or G. If we put identity, however, we will have a problem, because then we will have to put G here, because we'll have to have all the elements appearing in this second row, but then we'll have the column problem, because we'll have two G's in the last column. So that, as you can see, is very much like a Sudoku game, but it's way better because it works for any size and it doesn't really take much as the input. So with this argument we can be sure that here we only can put G, and hence the only option here will be the identity, and the same for the second column, it's the identity here, and finally the remaining empty spot can only be filled by F. So we proved again that groups of order 3 are effectively unique. It just takes a relabeling to identify the Cayley's tables. So let's look at the examples, real life examples of such groups of order 3. We have integers mod 3. If we label remainders mod 3 by 0, 1 and 2, the operation table, the Cayley's table, the addition table will look like that. And you can see it is identifiable with the template we have proven to be unique. So the second example we could put here is cubic roots of 1 in complex numbers, and we have 3 of them. So let's call the first the primitive epsilon, and then we have epsilon squared, which is also the primitive, and epsilon will be this e to the 2 pi I over 3 in earliest notation. So then the multiplication table for these complex numbers will, no surprise, be looking like it should, will be fitting the template. So here we must have epsilon squared, because it's just the product of epsilon with itself, and here we have epsilon cubed, which is 1. Here we have epsilon cubed again, which is 1. The operation is commutative, which results in the symmetry in this Cayley's table, and here we should have epsilon to the 4, which is as good as epsilon, because epsilon cubed is 1. So that is again a very satisfactory complete result about all groups of order 3. They have to be all the same, all isomorphic. If we look at groups of order 4, that will be the first place where 2 different answers are possible. I will not do it using Cayley's tables, I will not prove this fact. If you like, you can do it. It's rather bulky, but it's still manageable. I will just list 2 possible answers, the only 2 possible answers. So one is integers mod 4. You can see that this answer is always possible for any order. Now I have 4 remainders, and computing the addition, I will have this shifting pattern. So every next row will be obtainable from the previous by 1 step shift to the left. You can check that that is indeed the addition table modulo 4. The other example is, say, the multiplication table for invertible integers modulo 8. These integers again form a group of order 4 because there are 4 of them. 1, which integers are invertible modulo 8? Those which are coprime to 8, and coprime means just odd. So 1, 3, 5 and 7 are these integers, and this is a complete list of them. And when we compute what happens, this time every square is 1. So anything squared will be congruent to 1 mod 8. 3 squared is 9, it is congruent to 1 mod 8. And so is 5 squared, it is congruent to 1 because it is 25 and it is 1 plus 24. And so is 7 squared, which is 49, it is 48 plus 1. So here we have ones on the diagonal which are saying that the order of any element is 2 modulo 8, if it is not 1 itself. And then we can compute the rest of the table. So say 3 times 5 is 15, it's as good as 7 modulo 8, and here we will have 5. I will speed up the process. 7 again, 5, 3 and 3. So you see that this is a fundamentally different table to that one, simply because here we have an element of order 4. We have to add 1 to itself 4 times to get 0, and here any element composed with itself or multiplied by itself will give us the sorry, I said 1, so we have to add 1 to get 0 4 times. 0 is the identity element. In this case, the identity element is 1, and the order, let me just write, so the order of 1 modulo 4 is 4, and that means the additive order, the cycling behavior under addition. The order of anything, well, I will better write it as anything raised to the square is congruent to 1 mod 8, and that is the guarantee that orders cannot be 4, so these tables cannot be identified because the orders will then have to coincide for identified elements. Let me finish with the only possible answer for size 5. It's even bulkier, bigger by 1, but the answer will be unique. As before, as for 2 and 3, the only possible answer will be this cycling pattern of integers mod 5. Again, we can just start by repeating our sequence, which is the result of adding 0 to it. And then we can just see that we had 1, so we shifted to the left by 1 step. And the element which goes over comes back to the line, so we have 2, 3, 4, 0, 1, 3, 4, 0, 1, 2, 4, 0, 1, 2, 3, and you can check again at every place you have the correct answer for the addition module 5. And the next in line group, so for the 6, again there will be 2 answers. There will be this template cyclic answer, the integers mod 6, and there will be the symmetric group on 3 elements, which this time will have a non-symmetric multiplication table. It will be a non-abelian group. So definitely they're going to be different, but proving that there are only 2 possibilities is already a challenge. Doing it head-on with just Cayley's tables is not practical at all. See you later with more.